With this third lecture, we continue our study of polymer solutions.
So now, FLORY said, okay, there are two very interesting things there. One is, if the polymer in a good solvent, if the polymers, monomer of the polymers don't like each other, then we have a effect repulsion between them. However, it cannot go on swelling, because when you increase, remember the distribution is e to the power minus r square, where the r square comes because all the many configurations. What is the configurational degree of freedom tells you? It tells you of the entropy. Now you can see e to the power minus r square has a maximum. You have r equal to 0, but this, remember, this is an average because many different orientations. That's why r0 comes. But however, you also tells you cannot stretch it too far. This is called elasticity of the polymer. So polymer loses lots of, it loses a lot of entropy if you stretch it. So there is these two forces acting opposite to each other. One is that repulsion energy, which tries to push it out, but elasticity of the polymer, which wants to keep it at certain size. This is what FLORY realized, and he did a beautiful calculation. Okay, say, okay, internal concentration of the N by RT, as we discussed already. Then I can consider a repulsion energy with this equation that F repulsive is half kBT nu dc square. So this nu t is the effective parameter, and as I said, this is essentially nothing but van der Waals theory that we are doing. And so see, now here the important thing to know, two terms, nu t and let us know Vt, not nu, it's V. Vt, which is a temperature dependent excluded volume parameter, which is like, very much like the A parameter in van der Waals theory. That means it's a volume parameter, but it essentially takes care of the interaction energy. Now, and so C is the concentration, the number within a volume. So volume is R to the power D, number is N. So this is the repulsion energy. And FLORY introduced this parameter 1 minus 2x b to the power D, and we'll learn a lot about it later. But it's just to show that it can go either from plus to minus. And then integration over the volume element. If I integrate over this volume element of this C to N to the power RD, and then I get this quantity volume element, then I'll get the total repulsion energy is N square, because there is coming with a N here RD, and then I take all the monomers, then I get N square. So integration of volume element essentially meaning taking all the things. So the important thing is that repulsion energy scales as N square by RD. Now, if I take the elastic term, which again is coming, now it is nothing but what is in the exponent of the Gaussian distribution. So R square by ND square. That's what I had in the Gaussian distribution. So since e to the power Boltzmann distribution gives me a value of a quantity x, e to the power minus x by kBt. So I just rearrange terms, I get the elastic terms trivially, a kBt R square by ND square. So I have the repulsive term of n number of monomers connected in a polymer in a chain is n R square, n square by RD kBt V, and V is the van der Waals, essentially van der Waals A. And then, and it plays a very similar load of A, and comes out in a very similar way that we have already done Mayer's theory. When you do that, then we see, we add the two, free energy, repulsion and the elastic term, which is an effective attraction, which is kind of putting it closer together. When I add them, I get these things. Sorry, it's a little bit, but we'll give you the right. It's screwed up equation by V by N square by RD. That is where the Just two terms are added. Now, the important thing is that I minimize F with respect to R. And if I minimize R with respect to R, then I get a beautiful result. This is because when I have dr equal to 0, then there is a r to the power d plus 1 it becomes, and these terms become r. So d plus 1 and r, but they are in opposite side. One is numerator and is denominator. So when I rearrange the terms, then I get there is a negative comes from n square by rt and positive comes r square by. So they worked out right. So you get then r to the power d plus 2 scales as the n cube, and then you get the beautiful result RF. This is for FLORY, that n to the power nu, the radius of FLORY, the nu is called FLORY parameter 3 by d plus 2. That means, so when I get d equal to 3, it becomes 3 by 5. Very important result. D equal to 3, I get 3 by 5. So suddenly you see, in ideal polymer chain, this end-to-end distance scales as n to the power half, square root. In half, nu is half. However, when you take attraction and repulsions, all these things into account, and in a good polymer solvent, then you get this huge difference. That means n to the power half, because n to the power 3 by 5 in. But when you go to d equal to 4, another surprise and interesting result. D equal to 4, it is 3 by 6, equal to half. So in 4 dimension, that is very important. So theoretically, not much relevance in the real world, but you get this ideal chain behavior, partly because when you have 4 dimension, then the concentration of polymer, then is so much more volume around each polymer, then these repulsive interactions and all these things are not that important. That's why you get back the ideal polymer chain. But 3 dimension and 2 dimension things are very different. Now it is, we have discussed this before, so but I would like to emphasize it. RF is n to the power nu. For ideal chain, nu is half, but it is not so in A. So in the real chain, it is very, very different. Thermodynamics of polymer solution, we already did quite a bit, because at the end of the day, it's the same thing, that we will be having this, take care of these 2 forces. One is the interaction with the solvent, monomer solvent interaction. That's one term, which is, I already said, FLORY parameter chi, that will come here and will be a little bit more quantified here. And then we'll do the mixing of polymer in a solvent. So solvent has to come in. So in addition to the entropy that we talked about and polymer interaction, that you will have one more entropy. That entropy is a mixing entropy between the solvent and the polymer. So basically the entropic term here is essentially the arrangement of polymer chains that exist. So what one considers in FLORY-HUGGINS theory, very famous theory, that one considers that you have a lattice, and the lattice theory works very well in polymer, because polymer is so big, much bigger than solvent, that one can consider, as I told you, as a random walk. And that since the size of the monomer is not important, one can as well take the advantage of the lattice. So now we have to calculate that how many ways, or make an estimate how many ways I can put monomer, the polymers, monomers of the polymer and the solvent molecules on a lattice. And that will give an entropic term. And there's an enthalpic term because of interactions between solvent molecules and solvent and polymer monomer. So enthalpy will have 3 terms. And we already considered the effective interaction of these kind of good solvent versus poor solvent. Here is the same thing, and what we are doing is very similar, but we are doing a little bit more justification of the polymer or polymer solvent interaction. That is a little bit done better and quantify that. That's why otherwise nothing different from the what we did earlier, or same minimization of free energy and everything will come. So when we do that, we said how many ways I can put a polymer. Then you can see the first term and the second term on the right hand side. This is the free energy of mixing. And free energy of mixing as the entropy term. That means how many ways I can place a polymer n of size n, polymer size n, let's say np. N is the total number of sides. And then and calculate that is entropy of mixing, because I am mixing the solvent molecules and the polymer, and I'm laying down the polymer in the lattice. And how many ways I can do that? Essentially same as binary mixture entropy of mixing. When you do entropy of mixing in your thermodynamics in binary mixture, what you do n factorial divided by na factorial nb factorial, and then that gives you the omega, the total number of ways, and then you take log of that to get the entropy by using Boltzmann formula, and that gives you x1 ln x1 plus x2 ln x2. You can also write x1 ln x1 plus 1 minus x1 ln 1 minus x1, because x1 and x2 are mole fractions. Together they become 1. It's a very similar thing here in polymer. Here, however, one has to take care of the fact that you have a polymer is a monomer. So the first term, polymer consists of many monomers. The first term takes care of that fact. The second part is just the solvent part, and phi is the volume fraction. The size of the through phi enters the size of the polymer. Now the important thing, the chi, I said, is the FLORY parameter chi. That has exactly the same thing we have in binary mixtures. And we did the binary mixtures, or yeah, not, you look in my book, binary mixture has been done in great detail. That is the, if I A and B, then A interaction and AB interaction and BB interaction. When A and B like each other, then these parameters, that means monomer and of the polymer and the solvent, they like each other. Then the chi term that you see on the first term on the right hand side will be negative, and chi will become negative. On the other hand, if A and B here monomer of the polymer and the solvent, they don't like each other, then and A and B they like each other, then A like each other, BB like each other, then this term is becomes, because then chi and negative, then the chi becomes positive. So a good solvent, chi is negative, and a bad solvent, chi is positive. So through this parameter, we essentially what FLORY did, we used the ideas of entropy of mixing and the entropy of mixing and the binary mixture theory, the ideality, non-ideality parameter that we know in the breakdown of Raoult's law. So the idea of this classical physical chemistry is combined with statistical mechanics or statistical concepts to develop this statistical thermodynamic theory of polymer solution in a very elegant and very simple way, which has stood the test of time. So this again, the same thing, this is side, because I divide by total number of sides, and then you get the entropy of the solvent, as I said, and entropy of the things. I am not going through the derivations. You will find the derivations in many places, including my book and also in Wikipedia. There's a good theory of FLORY-HUGGINS. So now I want to calculate so I have calculated the entropy. This is the entropy of laying down a polymer into a lattice side. A polymer of volume fraction phi, lattice of n sides. That's why the first n in the denominator comes. Now monomer interaction, as we just discussed, is the van der Waals sum. There is kBt. I put kb equal to 1. kBt by the FLORY parameter chi for monomer phi square. Then monomer solvent, because monomer and solvent, it is phi into 1 minus phi, because 1 minus phi is for solvent, and solvent is 1 minus phi square. There are 3 terms. What I do now, I next add all these terms together and I keep, okay, I keep in the term which is linear. So I find out in that sense, it is the maximum contribution comes from the one that I need is the monomer solvent interaction is phi into 1 minus phi. So this becomes the important term. The first term becomes the important term for me in this understanding the thermodynamics of polymer, because solvent polymer interaction is chi phi 1 minus phi. Chi gives the relative interaction and phi into 1 minus phi gives the probability that a monomer is interacting with the solvent molecule. Then I add all these things together and then I again minimize. And when I minimize this free energy, then I get the theory of the polymer solution. And that theory, when I do with the value of chi, it is essentially Van der Waals theory that then explains this good solvent and bad solvent collapse in terms of these things. So the chi in the good solvent, chi is negative, but when it crosses over to poor solvent, then chi is positive. And this is exactly the thing that you get the free energy, and then you find out what is the side, and you find there's a crossover in the size from depending on the value of chi. Okay, this is the essentially this free energy embodies the thermodynamics of polymer solution and FLORY-HUGGINS theory. More details are worked out in my book. I'm sorry we don't have, but we'll try to put a slide there on these things. Next slide is missing, so I won't be able to go to that, but instead I'll go into something which is the FLORY-STOCKMAYER theory. This is the theory that we know experimentally when we are doing a transition, we find a transition. That means when I add many important thing, we need the gel, many of the applications of material. So what do? We go on adding the concentration in these monomers, and then we sometimes add some things, gel them together. But what happened when the monomer concentration goes beyond certain thing, concentration or temperature is lowered, then we find there's a dramatic transition, a phase transition that takes place from salt to gel. And that is called the salt-gel transition. Is a very well-known phenomena, which is essentially very close to what we do in Mayer's theory. So salt-gel transition is very similar to gas-liquid transition. And the reason of my including in this course and also in the book is that to show you how Mayer's theory is used. Mayer's theory of 1937, and FLORY did almost at the same time, and STOCKMAYER did it later in 1941. The same theory. STOCKMAYER was a student of Joseph Mayer. So basic idea that that instead of Mayer's clusters, we have the real polymer clusters. And you remember the Mayer's theory, two guys come close to each other and we have a Mayer F function. Here we have the Mayer F function is replaced by something called functionality F. And the polymers like nylon, they never form, they are thread-like, they never form a gel, but they become very long. And it is important that they don't form a gel for all our textiles. But in many other cases like rubber, we want them to form a gel. And that is when functionality has to be greater than 2. So I briefly tell you now method of sol-gel transition, and there is a basic idea then is that I have a solution phase where viscosity is low and monomers are kind of dispersed, and then they undergo a polymerization and they form a giant molecule and they precipitate out. The reason it is important to understand it, because the sol-gel transition, if we can control the property of the gel, which is very, very. And so this exactly it follows like Mayer's theory, a system of n identical monomers and carrying identical functional groups. So monomers react with each other to form a polymer, and the functionality is F. It's chosen very similar to Mayer's F function, also functionality F. Now we have to say after at some stage of the polymerization, we have Mn gives the number of monomers of size n, and then sum of Mn, the last equation in the bottom, is the total number of polymers, and Nmn is the total number of monomers. This is exactly what we did in Mayer's theory. The Mn is the number of n clusters of Mayer, Nmn is the total number of molecules or atoms, the system name, and then Mn is there also. The capital M was the size of the polymer. Okay, so the total number of ways. Now we do exactly what Mayer did. So we can remember what we did, the Mayer's partition function, Qn. Here that is the number of ways I can form monomers, dimers. And so this is our essentially our partition, omega is partition function Q. And in this sol-gel transition, the interaction is already taken into account by forming monomer bond. As I told you, that is essentially Mayer function. So all we need to find out how many ways I can form these things, and then that exactly Mayer's theory, omega n to the power omega n by n factorial. Omega n is what we call BL or Mayer's cluster integrals. So it is exactly Mayer partition function. And then we need to know what is the Mayer BL. Remember in Mayer's theory, we did omega n or BL in terms of the irreducible cluster integrals beta n. So that is now done. In this case, the omega n is evaluated, one can evaluate it directly, and that is given here. The story goes in the following. In Mayer's theory, I told you the relation between cluster integrals. The Mayer did the expression of the Mayer cluster integral Q in terms of reducible cluster integral BL, but the derivation of BL in terms of beta K was highly non-trivial, and that was done by his wife Joseph and the Maria Goupart Mayer, who got the Nobel Prize later in nuclear shell theory, and who didn't have a job, because those days women, it was very difficult for women to get a job. So and she came from America and then was in Columbia for some time. They moved to Chicago. Even in Chicago, she was not given a job in the beginning. But it was the Maria Goupart Mayer who helped STOCKMAYER, which is in STOCKMAYER's 1941 paper. That is acknowledged. But she didn't want to become a co-author of the paper. So omega and neither was she co-author of the Mayer's paper. So those days, the women many times did not get the due credit they deserved. That is something which one of our famous scientists, Dan Franken, repeatedly brings out these days. That many of the things in the old days were done actually by women, and that were not given much credit, but whatever. So this is the expression in terms of the F and N, and when you do that, put this into that should be Fn in a mistake, Fn minus 1 factorial. So there are 2 factorial, actually 1 factorial sign is missing. But when you do that now, you have to do exactly like in Mayer's theory. You know, I now maximize the omega. That's this thing, you know, in statistical mechanics. It's the same as minimization of free energy. Maximization omega is same as maximization of entropy. And that is same as minimization of free energy. And when you do that, I get a beautiful relation, which is in terms of the most probable distribution, which is actually parallels the one Mayer's ML Mayer's theory. That has now, that where there comes a fugacity in Mayer's theory, here that quantity is by zeta. And beauty of that, I can now evaluate A and zeta. And the A is the following expression, what you have. If n1 minus alpha square by alpha, and alpha is the extent of reaction, very common in chemistry. That means how many the number of functional groups react. So if I don't have ring, that's why absence of ring polymer cyclization comes as an hypothesis. So then alpha is 2. You can easily convince yourself this is the fraction of because each reaction consumes 2 functional groups. That's why you see the factor of F. Total number of functional groups is Fn. So extent of reaction 2n minus m by Fn. That is the extent of reaction. And when I do the minimization with Lagrangian multiplier, then I get the F n1 minus alpha square by alpha. So one does exactly Mayer's theory. One does the Lagrangian multiplier, parallel all these things. Then now I got the Mn or Mn star. Now I can do some science. What we measure in experiment, like in viscosity, is the weight average molecular weight. That viscosity diverges. So I now do, first I define, okay, I know Fn. So I do what is the weight fraction of an NMR, which is exactly like LML in Mayer's theory. What is the weight of the gigantic cluster that is going to appear? Here, what is the weight of NMR? That is Mn by N. And then I put this Mn expression here, last equation, and I use the A here, and then I get made a small transformation of variable zeta to the power n. There's f to the power n comes, that becomes x to the power n on the extreme right of my right hand side equation. And Fn minus n factorial, as I said, there's a there. So that is Wn. Okay. So I go by, I want to correct it a little bit. This is f to the power n. The n that is subscript here should be superscript. Is a power. Okay. Then I get this equation. Then now weight average molecular weight, if this is the omega Wn is a distribution. So in order to get the normalized distribution, I have to multiply it by n and sum over Wn over all n. Multiply by W and sum over all n. When I do that, this sum can be done. And this is one of the another tour de force and a beautiful result of statistical mechanics, that I get this beautiful expression of weight average molecular weight, which is observed by light scattering, observed by viscosity, and all other experiments. Now look at this beautiful equation. There's something very nice about this equation and some unusual. When alpha into f minus 1 equal to 1, I repeat, when in the denominator on the right hand side, extent of reaction increases such that alpha into f minus 1 become 1, then the denominator diverges. So when the extent of reaction becomes 1 over f minus 1, then f minus 1 alpha equal to 1. So that extent of reaction, when monomers react to that extent, increase as it is going on reacting, reaches 1 over f minus 1, that value, then it diverges. And that is exactly what is shown here, that that the weight average molecular weight is undergoing a divergence. So plot of a system of trifunctional unit where this becomes this extent, it diverges, and extent of reaction in trifunctional unit F is equal to 3. So 3 minus 1 is 2. So 2 into alpha. When alpha become half, then for a trifunctional unit, this diverges. This is where you find this divergence into the things. It is exactly like similar to density theory. Now, so summary of this. So this is essentially same as appearance of a liquid phase, and this is one of the beautiful theory where FLORY used it first, then STOCKMAYER did it. And as so, we need to, I just briefly summarize you polymer that we done. We have done the end-to-end distribution and polymer size. Then we have done theory of polymer solution, which has been remarkably successful, and it can explain polymer swelling. It can explain polymer collapse. It can say this crossover from swelling to collapse at the theta temperature. And FLORY-STOCKMAYER theory of sol gel transition, essentially the application of from Mayer's theory to polymerization. And STOCKMAYER was a student of Mayer, but also worked with FLORY, and he said, but FLORY already did that sol gel transition. FLORY did that before, but STOCKMAYER used to make it more rational by using the Mayer's theory, and that's very nice. And as I told you, FLORY was given Nobel Prize, single Nobel Prize in 1974. People say Falkenstein should have shared it, but given the FLORY's contribution so gigantic, because he not only did the theory of polymer size distribution, the theory of non-ideal polymer, that is n to the power nu equal to 3 by 5. He did the theory of polymer solution, which is FLORY-HUGGINS. Then he did the sol gel transition, that is also FLORY theory. So that is probably was justified to give FLORY this single Nobel Prize. To summarize, I want to tell you that this theory is essentially almost like the one that we did in the course is essentially a celebration of FLORY, Paul FLORY, who, as I told you in the beginning, was a remarkable human being, who not only just did this wonderful work, he did work in many other areas, biology, and many places. The FLORY theory, FLORY is, that's why is also very important and respected name in biology. And he's a humanitarian who did a lot of work for scientists in underdeveloped countries and under difficult conditions. So look up the FLORY's theory of polymer. Look up Dijan's book of scaling concepts in polymer physics, which takes many of the FLORY concepts to a much higher level. And last I say that one of the reasons probably FLORY was given in 1974 Nobel Prize, though many of his work were done before 1940s and 1950s. The reason was that in early 70s, just after critical phenomena theory was developed by Kenneth Wilson, Ben Wiedom, Michael Fisher, and all these people, and that is the time 1972. Dijan did a wonderful calculation of polymer excluded volume. He mapped it into a magnetic problem, and he could essentially do renormalization group calculation of the polymer problem. Then Michael Fisher extended that, and they discovered all the FLORY equations, all of them. They discovered that yes, mean square size scales as n to the power nu, and nu is 3/5 for 3 dimension and half for 4 dimension. Then they discovered the theta solvent, polymer collapse. So whole of FLORY theory was developed and derived by using much sophisticated methods of polymer physics by Michael Fisher and some other people in France and Germany. And that probably then the realization that this, what FLORY did, goes far beyond just a polymer. It is a beautiful theory of statistical mechanics, a contribution to statistical mechanics, multiple contribution to statistical mechanics of interacting system. Okay, I stop here today. This is the last lecture on polymer, and I strongly recommend you to read our book, my book, and the other 2 books also. Okay, I hope you enjoyed, and thank you for your attention. Bye.